Greetings to one and all present here. My name is Poornima. I'm currently doing my doctoral degree at the Department of Environmental Sciences, Tamil Nadu Agricultural University. And I'm hereby presenting a part of my research work on screening protectants to mitigate the ozone stress on rice cultivars. So climate change has been creating a greater impact on the human health, agricultural productivity, and food security. Hypospheric ozone is one such phytotoxic secondary air pollutant whose concentration has been inadvertently increasing since the Industrial Revolution. So the phytotoxic impact of tropospheric ozone has been well documented, and it has been projected that the economic loss due to the tropospheric ozone would be around $6 billion in maize, $18.8 billion in soybean, $10.6 billion in rice, and $12.5 billion in wheat. So, with one of the main goal of sustainable development goals being the climate action, so mitigating or alleviating the effect of tropospheric ozone on yield loss in various crops has been gaining significant importance in the scientific community. Asia is the world's greatest emitter of the two major precursors, namely the nitrous oxide and non-methylated volatile organic compounds, which are majorly involved in the formation of tropospheric ozone in the presence of sunlight. And India contributes around 11 to 13% of the precursors worldwide. There are many studies that have been conducted in estimating the amount of tropospheric ozone in various parts of the country. And all studies suggested that the tropospheric ozone concentration would soar up to 13% by the year 2050. Hence, there are various strategies like altering the fertilizer application or offsetting the nitrous oxide emission by adopting no-tillage practices or developing a tolerant variety through marker-assisted selections or breeding technologies or application of phytoprotectants, or it can also be mitigated by changing the potassium levels. Nevertheless, all these strategies have their own limitations. Amongst all these strategies, application of protectants seemingly to be the most cost-effective and easily available technique in alleviating the effect of tropospheric ozone on crops. So in our study, we have chosen rice as the test crop since it is one of the most staple crop in India with a production of around 127 million tons during the year 21 and 22. And TRB2 is one of the most predominantly growing rice variety in Tamil Nadu, and previous studies have reported that TRB2 is one of the variety which is very sensitive to ozone. So this is the reason why we have chosen TRB2 as the test cultivar in our study. And we have chosen 7 different protectants, namely the ethylene diurea, neem-coated urea, calcium acetate, ascorbic acid, neem oil, panchagavya, and pink pigmented facultative methylotrophs. The choice of these antioxidants or protectants are based on the literature studies, and the exposure of ozone was given around 100 ppb. The choice of ozone concentration was predicted to be 100 in the near future, and this is the reason why we have taken 100 ppb. And during the exposure was given during the critical period, that is during the active tillering and panicle initiation, which falls from 51 days after sowing to 80 days after sowing. TRB2 being a short duration variety of having a duration period of 115 to 120 days, the active tillering stage will usually begin from the 51 days. So the ozone exposure is given during the critical period, and the protectants were given through foliar application at 6 days interval. And the changes in the physiological traits like the photosynthetic traits, tomatal conductance, and chlorophyll content were observed. The ozone was fumigated through an ozone generator, which works on the principle of high frequency coronal discharge technology. So the results indicated that in the control where there were no application of any protectants, the leaf injury percentage and leaf bursting score was significantly higher. However, application of these protectants significantly nullified or reduced the leaf injury percentages, and the least leaf injury percentage was recorded with the application of 300 ppm ethylene diurea. Initially, irrespective of the treatments, the leaf injuries were not visibly seen during the initial stages of ozone fumigation. That is, let us say, for the first 10 days, no visible injury was observed. Whereas while prolonging the ozone exposure, like up to after 20 or 25th day, the visible injury was very prominent and very intense in case of control compared to those receiving the protectants. So all these data were collected only after 30 days of ozone exposure, and the photosynthetic rates, tomatal conductance, and chlorophyll content was also observed to significantly decline due to the exposure of ozone. However, the application of protectants increased the photosynthetic, the stomatal conductance, and chlorophyll content, and the highest physiological traits were recorded with the application of ethylene diurea, which was followed by the 1% neem-coated urea and ascorbic acid, and both were on par with each other. So nitrogen addition, this particular increase in the physiological traits due to the application of protectants like ethylene diurea and neem-coated urea might be because due to the application of nitrogen. So the nitrogen addition may increase the leaf turnover, resulting in the formation of new leaves with high photosynthetic potential, preventing the decreased photosynthesis caused by the ozone damage in the older leaves. In case of ascorbic acid being itself an antioxidant might have facilitated the detoxification of the reactive oxygen species, thereby nullifying or reducing the damage that is being caused by the ozone. So, to conclude, irrespective of the phytoprotectants that is being studied, amongst all the protectants under study, EDU performed the best. However, due to the unavailability, besides EDU, neem-coated urea and ascorbic acid seems to be the cost-effective and easily available protectant that can be used to mitigate or alleviate the loss that is being caused due to the ozone exposure. A common mechanism that involves in the alleviation might be because the carbon assimilation rate might have increased with the increase in photosynthetic efficiencies of the plant, thereby which will reduce the yield loss that is being encountered due to the exposure of tropospheric ozone at higher concentrations. Thank you.